transformations, but before I expose you to them, I'm highly interested in testing your memory about these three transformations. How much do you remember them? For that, I have a question for you. So let's check that out. In this question, if you take a good read at it, you are given a closed interval 0, 3 pi, and in this interval, you have to find out how many points of intersection are there of 2 sine x and cos x by 3. That means your agenda is basically to plot the graphs of 2 sine x as well as cos x by 3 in the same Cartesian plane, then catch hold of all the points of intersection of both these graphs and report your answer. Okay? So let's begin with plotting the graph of the first function 2 sine x. Well, you would definitely agree that if I take f of x equal to sine x, then 2 sine x is nothing but twice of f of x. Yes, I know the graph of f of x, but I want to sketch the graph of twice of f of x, where 2 is obviously a constant greater than 1. Can you recall something? Well, this is obviously the case of vertical stretch transformation, which says that multiplying a constant greater than 1 to the output of f of x is equivalent to vertically stretching the graph of f of x a times along the y-axis. Okay, so we are going to plot the graph of f of x equal to sine x only in the interval 0 to 3 pi. Mind it, okay? We don't want the graph in the remaining part of the real line. Got it? So this is the graph of sine x in the interval 0 to 3 pi. Now, I will be vertically stretching this graph along the y-axis twice. When I do that, I end up getting this to be the graph of 2 sine x. Okay? And the logic is extremely simple. I have already explained this to you before. I'll repeat it. If corresponding to an input x, y is the output of sine x, then corresponding to the same input x, 2y is the output of 2 sine x. That is the reason why at pi by 2 sine x is 1, whereas at pi by 2, 2 sine x is 2. That is twice of 1. At 3 pi by 2, sine x is minus 1, whereas at 3 pi by 2, 2 sine x is twice of minus 1, which is minus 2. At 5 pi by 2, sine x is 1, and at 5 pi by 2, 2 sine x is twice of 1, which is 2. Obviously, the points at which sine x is 0, 2 sine x is also 0. That is why the points at which the two graphs are intersecting the x-axis are exactly the same. Because of this logic, when I vertically stretch the graph of sine x, by 2 times, I get the graph of 2 sine x. Let's now move on to plotting the graph of cos x by 3. Well, again, if I take f of x as cos x, you would agree that cos x by 3 is nothing but f of x by 3. Yes. Now, I know the graph of f of x very nicely. We've learned, right? I want to sketch the graph of f of x by 3, where 1 by 3 is a fraction between 0 and 1. Can you recall something? Well, obviously, this is the case of horizontal stretch transformation. What does it say? It says when a fractional value is multiplied by the input of a function, it is equivalent to horizontally stretching the graph of that function f of x a times along the x-axis. Okay, so I'm going to plot the graph of cos x in the interval 0 to 3 pi. That is our interval of interest. Just keep that in mind, okay? I've plotted the graph of cos x in the interval 0 to 3 pi. Now what will I do? I will stretch this graph horizontally along the x-axis 3 times to get the graph of cos of x by 3. When I do that, this is what I get. Let's understand the reason behind this, okay? See, in the interval 0 to 3 pi, for the first time, cos is 0 at pi by 2. So in the interval 0 to 3 pi, cos x by 3 will be 0 for the first time at thrice of pi by 2, which is 3 pi by 2. Can you see here? Yes. Similarly, in the interval 0 to 3 pi, cos x is minus 1 for the first time at pi. So in the interval 0 to 3 pi, cos x by 3 will be minus 1 for the first time at 3 times pi. Justified, and there's no point of discussing further because I'm only interested in the graph in 0 to 3 pi. So bingo, this is what justifies the graph of cos x by 3. Now that I have the graphs of 2 sin x as well as cos x by 3 with me, I'm going to plot them simultaneously in the same Cartesian plane. And when I do that, what do I get? I get 1, 2, 3. These 3 explicit points of intersection. I'm not interested in their coordinates. I'm just interested in the number of points of intersection because that is what the question asked. And hence, my answer is option C, that is 3. Now take a look at this question. It says, find the total number of solutions of this given equation in the open interval 0, 2 pi. That means we have to find out the total number of real values of x sitting in this interval which are able to satisfy this given equation. Now, before I directly take you to the solution, let me tell you the approach of solving such questions. See, whenever you are given an equation of the form f of x equal to g of x and you are asked to find out the total number of real solutions of this equation, the deal is extremely straightforward and simple. You just plot the graph of both f and g together in the same Cartesian plane, and once that's done, you move ahead to count the number of points of intersection of both the graphs. As many as there are points of intersection, those many are the real values of x which are able to satisfy this given equation, and hence you get your answer. This is the exact same strategy I'm going to adopt in this question as well. Let me take this as f of x and let me take this as g of x. I am going to plot the graphs of both f and g together in the same Cartesian plane only in the interval that I am interested in, which is open interval 0, 2 pi. Once I'm done with this, I'm going to go and count the points of intersection of both the graphs. Whatever that number comes out to be is going to be my final answer, because that number is going to represent the number of real values of x in the open interval 0, 2 pi which are able to satisfy this given equation f of x equal to g of x. Got the drill? Let's start. First step is plotting the graph of f individually. F is nothing but log x to the base pi. Now you know as a matter of fact that the graph of log has two variations. One corresponding to base being greater than 1, other corresponding to the base being strictly sandwiched between 0 and 1. Right now the base is pi, which is approximately 3.14, which is obviously greater than 1. That means the graph of log x to the base pi will look like this. Okay, obviously it is going to intersect the x-axis at 1, 0 because log 1 to the base pi is equal to 0. And also log pi to the base pi is going to be 1. Yes, log pi to the base pi is equal to 1. That means at pi, log is going to take the value 1. Remember, I'm only interested in the graph of f in the open interval 0, 2 pi. Now at 2 pi, let's say this is the value which log takes because the interval is open. That's why log 2 pi to the base pi is the value that I'm not going to include. Right? So in the open interval 0, 2 pi, this is the portion of the graph that I am interested in. Got it? Similarly, let's plot the graph of the function g of x in the interval 0, 2 pi open. Okay, this is the graph of cos function in the open interval 0, 2 pi. Because 0 and 2 pi both are excluded from the interval, corresponding to 0 the value 1 as well as corresponding to 2 pi the value 1, both will be excluded. Got it? This is my graph of the function g. Now what I'm going to do? I'm going to plot both the graphs together in the same Cartesian plane in the open interval 0, 2 pi. Well, here they are. Now what I have to do, I have to count the points of intersection, the number of points of intersection of both the graphs. So right now, evidently, I can see only one point of intersection. Yes? So can I justify this, that there won't be any other point of intersection apart from this? Let's justify. See, at pi, cos takes the value -1. Agreed? And at pi, log is taking the value 1. Beyond pi, log is going to be greater than 1. But wait a second. Cos is never ever greater than 1. The maximum value of cos function is equal to 1. That means beyond pi also cos is never ever going to be greater than 1. That means there's no scope of both the graphs intersecting beyond pi. Got it? Also before pi, the behavior of both the graphs is pretty evident over here. One is this and the other is this. So of course, they are going to intersect at a single point, and hence it's justified that in the complete interval 0, 2 pi open, there's exactly one point of intersection of both the graphs. That means in the open interval 0, 2 pi, there is exactly one and only one value of x, which is able to satisfy my equation log x to the base pi equal to cos x, and hence this given equation has only one real solution in the open interval 0, 2 pi, which makes you mark A as the correct option. Moving on to the next transformation, it is vertical shift. The question which this caters to is how to draw the graph of f of x plus a or f of x minus a from the graph of f of x if a is some positive constant. To get the answer of this question, let's take the help of an example. Suppose I have the graph of f of x equal to sin x with me, and I want the graph of f of x plus 1, which is obviously sin x plus 1. So in here I am taking a to be equal to 1, which is positive. To get this graph, for now, let me use the conventional approach. I'm going to plot few points which lie on this graph, then I'm going to join the points to get the graph. So let's begin. If I take x as 0, sin x plus 1 comes out to be sin 0 plus 1, which is 0 plus 1, which is 1, giving me the point 0, 1. Next, I take x as pi by 2. So sin x plus 1 comes out to be sin pi by 2 plus 1, which is 1 plus 1, which is 2. Next, I take x as pi, so sin x plus 1 becomes sin pi plus 1, which is 0 plus 1, that is 1. Next, I take x as 3 pi by 2, so sin x plus 1 comes out to be sin 3 pi by 2 plus 1, that means minus 1 plus 1, which is 0. Lastly, I take x as 2 pi, so sin x plus 1 becomes sin 2 pi plus 1, which is 0 plus 1, which is simply 1. When I join these points, this is the graph of sin x plus 1 that I get. So right now I have both the graphs sitting in the same Cartesian plane. On comparing, I notice something very interesting. I see that the pink graph is nothing but a shifted version of the green graph in the upward direction. Do you agree? In fact, to be precise, if I take the graph of sin x and I shift it vertically in the upward direction, by 1 unit, I am going to get the graph of sin x plus 1. And this is not just a random observation, there is logic behind it. If corresponding to an input x, y is the output of sine x, then corresponding to the same input x, y plus 1 is going to be the output of sine x plus 1. Right? That's why shifting the graph of sine x vertically in the upward direction along the y-axis by 1 unit is going to give you the graph of sine x plus 1. Now, exactly in the same fashion, if I have the graph of f of x equal to sine x with me, and I want the graph of f of x minus 1, which is obviously sine x minus 1. Okay, so in here again, I'm taking a to be equal to 1, which is positive. Then using your conventional method, when you plot this graph, it will come out to be this, which is nothing but a shifted version of the graph of sine x in the downward direction by, again, 1 unit. Yes, that means if you take the graph of sine x and you shift it vertically downwards along the y-axis by 1 unit, you are going to get the graph of sine x minus 1. Now, to get a better feel of what's happening in here, let's check out a simulation. Similarly, if this is the graph of sine x plus a, where a is equal to 0, that means this is the graph of sine x. Now, as a is getting smaller and smaller, lesser and lesser than 0, what is happening, can you see? The graph of sine x is shifting more and more vertically in the downward direction. So this means what? That subtracting a positive constant a from sine x is equivalent to shifting the graph of sine x vertically downward along the y-axis by a units. And that's how adding or subtracting a positive constant a to sine x results in the vertical shift of the graph of sine x. In fact, this is not just valid for sine x, this is actually valid for any function f. Adding or subtracting a positive constant a to f results in the vertical shift of the graph of f. If you are adding a positive constant a to f, that is equivalent to shifting the graph of f along the y-axis in the upward direction by a units. And if you are subtracting a positive constant a from f, it is equivalent to shifting the graph of f along the y-axis in the downward direction by a units. Got it? Coming up next is the transformation horizontal shift. The question which this transformation caters to is how to draw the graph of f of x plus a or f of x minus a from the graph of f of x, where a is again some positive constant. To answer this question, let's take the help of an example. So in here I have the graph of f of x equal to sine x with me, and I want to sketch the graph of f of x plus pi by 4, which is obviously sine of x plus pi by 4. In here you can see that I am taking a to be pi by 4, which is a positive constant. Well, let's use the conventional method to do so. I'm going to plot few points, then join those points to get this graph. So let's begin. If I take x as 0, sine x plus pi by 4 becomes sine pi by 4, which is 1 by root 2, giving me the point 0, 1 by root 2. Next, I take x as pi by 4. So I get what? Sine of pi by 4 plus pi by 4, which is sine pi by 2, which is 1. Next, I take x as 3 pi by 4. So that gives me sine of 3 pi by 4 plus pi by 4, which is sine of 4 pi by 4, which is sine pi, which is 0. Yes. Next, I take x as 5 pi by 4. So sine of x plus pi by 4 becomes sine of 5 pi by 4 plus pi by 4, which is 6 pi by 4, which is 3 pi by 2. And we know sine 3 pi by 2 is minus 1. Lastly, I take x as 7 pi by 4. So I get sine of 7 pi by 4 plus pi by 4, which is sine of 8 pi by 4, which is again sine 2 pi equal to 0. When I join these points, this is the graph of sine of x plus pi by 4 that I get. Now that both these graphs are sitting in the same Cartesian plane, on comparing, I notice that actually the pink graph is nothing but a shifted version of the green graph towards the left along the x-axis. Isn't it? In fact, you know what, to be precise, if I take the graph of sine x and I shift it to the left along the x-axis by pi by 4 units, I am going to get the graph of sine of x plus pi by 4. That's the fantastic observation. In fact, in the same fashion, if I have the graph of f of x equal to sine x with me, and using my conventional approach, I plot the graph of f of x minus pi by 4, which is sine of x minus pi by 4, it comes out to be this, which is nothing but again shifted version of the graph of sine x, but this time to the right along the x-axis. In fact, again, to be precise, if you take the graph of sine x and you shift it to the right along the x-axis by pi by 4 units, you are going to get the graph of sine of x minus pi by 4. So what is happening actually? To get a better feel of this, let's check out this simulation. Similarly, right now the graph that you can see is sine of x plus a, where a is equal to 0, right? That means the graph of sine x. If a takes the value minus pi by 4, what just happened? The graph of sine x shifted to the right along the x-axis by pi by 4 units. Now I'm taking the value of a to be minus pi by 2. What just happened? The graph of sine x shifted to the right along the x-axis by pi by 2 units. And now I'm taking the value of a as minus pi. Oh my God, what just happened? The graph of sine x again shifted to the right, and this time by pi units. That means if you shift the graph of sine x to the right along the x-axis by a units, you will get the graph of sine of x minus a. In fact, the good news is that this is not just confined to sine x. In fact, this is valid for any function f. If you take the graph of f and you shift it to the left along the x-axis by a units, you will end up getting the graph of f of x plus a. Similarly, if you take the graph of f and you shift it to the right along the x-axis by a units, you will end up getting the graph of f of x minus a. Hence, to sum it up, adding or subtracting a positive constant a from the output of a function is equivalent to shifting the graph of that function vertically either upward or downward by a units. And that is why this transformation is called the vertical shift. Similarly, adding or subtracting a positive constant to the input of a function results in the graph of that function shifting horizontally to the left or to the right by a units. That is why this transformation is named horizontal shift. Got it? Next up is the transformation which involves getting the graph of mod f from the graph of f. How does this happen? Let's understand from an example. So in here I have the graph of f of x equal to sine x with me, and I want to sketch the graph of mod of f of x, which is mod sine x. Recalling the concepts of the mod function, we can say that the behavior of mod sine x will be same as the behavior of sine x whenever sine x is non-negative, and the behavior of mod sine x will be equal to negative of the behavior of sine x whenever sine x is negative. Well, graphically, function being non-negative means that its graph is on and above the x-axis, and function being negative means that its graph is below the x-axis. You can clearly see that from 0 to pi, the graph of sine is on and above the x-axis, so this portion will remain as it is in the graph of mod sine x. But from pi to 2 pi, you can see that in this interval, the graph of sine is below the x-axis. So its negative will be the graph of mod sine x in this interval. Negative of a graph means what? You have to vertically flip this graph about the x-axis. Yes, when you do that, this is what you get as the graph of mod sine x in pi to 2 pi, and eventually this complete pink graph is the graph of mod sine x. Do you understand? So if I generalize, what can I say? That in the graph of f, if you retain the portions which are on and above the x-axis and you vertically flip the portions which are below the x-axis, you are going to end up getting the graph of mod of f of x. Easy, right? Well, it's now time to check out this question. Take a look at it. It is asking us to find out the total number of solutions of this given equation in the closed interval minus pi comma pi. That means we have to count how many real values of x exist in this interval which are able to satisfy this given equation. So let's begin by carefully examining the given equation. Is there any scope of simplifying it further? Let's see. I can see a lot of mod cos x present here. I know as a matter of fact that cos x is real for every x real. Yes, this obviously means mod of cos x is also real for every x real. Okay, and you know real minus 1 is real. Twice of real minus 1, again real. Thrice of a real quantity minus 1, again real. So actually if you look at the left hand side, it is kind of like a into b into c equal to 0, where a, b, c are three real numbers or three real quantities. Product of three real quantities equal to 0 implies what? At least one of them has to be 0, right? That gives you either the first factor is 0, which is giving you mod cos x is equal to 1, or the second factor is equal to 0, which gives you mod cos x equal to half, or the third factor is equal to 0, which gives you mod cos x equals 1 by 3. So now the question has converted to what? Let me tell you. I have to find the number of real values of x in the interval minus pi comma pi which satisfy mod cos x equal to 1. Let's say that number is n1. I have to find out the number of values of x in the interval minus pi comma pi which satisfy mod cos x equal to half. Let's say that number is n2. Similarly for this equation, let's say the number is n3. In the end, I'm going to add n1, n2 and n3 and that is going to be my final answer. Because I want all possible values of x in the interval minus pi comma pi which are able to satisfy my given equation. That's why I'm adding all these three numbers up in the end to get the final answer. But the question arises, how to get n1, n2, n3? For that, let me remind you of a concept which I've already taught you. Suppose you have an equation of the form f of x equal to g of x. And you have to find the number of solutions of this equation. Basically, how many values of x satisfy this given equation is what you are trying to find. Then the deal is very simple. Just plot the graph of both f and g in the same Cartesian plane and catch hold of the number of points of intersection of the two graphs. As many as there are points of intersection of the two graphs, those many are the solutions of the given equation. Got it? This is the same strategy we're going to use in this question. What are we going to do? We are going to plot the graph of mod cos x as well as the constant function y equals 1, y equals half, y equals 1 by 3. All these we're going to plot in the same Cartesian plane. Then the number of points of intersection of mod cos x and y equals 1 will be equal to n1. The number of points of intersection of the graphs of mod cos x and y equal to half will be n2. And the number of points of intersection of the graphs of mod cos x and y equal to 1 by 3 will be n3. Once we've obtained n1, n2, n3, you know what to do. Just add them up. That's your answer. So let's begin. We'll begin with plotting the graph of mod cos x. Got it? Let's start. For plotting the graph of mod cos x, I first of all should be aware of the graph of cos x. Yeah, I already know how does the graph of cos x look like. And mind it, I'm only interested in the graph of cos in the interval minus pi to pi. Okay, that's why the graph is not drawn beyond these 2 points. How to get mod cos x from cos x? Well, we've learned this. Just retain the graph of cos x which is on and above the x-axis. Okay? And whatever is the part below the x-axis, vertically flip it about the x-axis. So I'll vertically flip this part, and bingo, that's how I obtain the graph of mod cos x in the interval minus pi to pi. So I have the graph of mod cos x with me. In the same Cartesian plane, I will be plotting the graph of y equals 1, y equals half, and y equals 1 by 3. But wait a second. Before I do that, realize that this point is 1. Okay? The maximum value of mod cos x is also equal to 1. So all these sharp edged points that you can see, they all have y coordinate as equal to 1. 1 is the maximum value of mod cos x. Okay? Now start drawing the graph of the constant function y equals 1. It will come like this. Yes. How many points of intersection can you see of both these graphs in the intervals minus pi to pi. Of course, this. So 3 points of intersection, that means n1 is equal to 3. Next, let's plot the graph of the next constant function, which is y equals half. So if this is 1, this is going to be somewhere half, okay? How many points of intersection can you see now of mod cos x and y equals half? Well, it's simple. 1, 2, 3, 4. That means n2 is equal to 4, isn't it? Similarly, now I'm going to plot the graph of this constant function y equal to 1 by 3. So if this is 1 by 2, this is going to be somewhere 1 by 3. Yeah. How many points of intersection can you see of mod cos x and y equals 1 by 3? Let's see. 1, 2, 3, 4. That means n3 is equal to 4. What to do next? 3 plus 4 plus 4. That's 11, isn't it? That means you get 11 points of intersection as a result of this. So what do you obtain? 11 solutions or 11 values of x, real values of x exist in the interval minus pi comma pi, closed interval minus pi comma pi, which are able to satisfy this given equation, and hence out of the given 4 options, D comes out to be the correct option. Interesting, isn't it? Time to take a look at another question. It says, find the total number of solutions of this given equation. If you take a look at the equation very carefully, left hand side is mod of cos x, let's call it f of x, and right hand side is a basic quadratic function, let's call it g of x. Finding the number of solutions of the equation f of x equal to g of x is equivalent to plotting the graph of both f and g in the same Cartesian plane and just finding out the number of points of intersection of both the graphs. So that is what we're going to do. We're going to plot the graph of both mod of cos x as well as x square plus x plus 1 in the same Cartesian plane and find out the number of points of intersection of both the graphs. Let's begin. First of all, I am going to plot the graph of cos x, okay? Don't forget, I want the graph of mod cos x. How to obtain the graph of mod cos x from the graph of cos x? We've learned that, well, retain the portion of the graph of cos x which is on and above the x-axis. And the portion which is below the x-axis, just vertically flip it about the x-axis. Let's do that. Okay, so this is how I get the graph of mod cos x with me. Next, I move ahead to find the graph of g of x, which is this standard quadratic function x square plus x plus 1. When I compare it with ax square plus bx plus c, it's very simple. A comes out to be 1, b comes out to be 1, c comes out to be 1 on comparing the corresponding coefficients. Leading coefficient a is positive. That means the graph of this particular quadratic function is going to be definitely an upward opening parabola. Next step, find the discriminant. It's b square minus 4ac. Plug in the values. You get discriminant coming out to be strictly negative. That means this upward opening parabola will nowhere intersect the x-axis. So this upward opening parabola will be strictly above the x-axis throughout. What will be its vertex? Well, minus b by 2a comma minus d by 4a. Plug in the values of b, a, d. All of the values you have, it comes out to be minus 1 by 2 comma 3 by 4, which is minus 0.5 comma 0.7 approximately I can write. Also, one more additional thing that we are interested to know is what is the point where the upward opening parabola is intersecting the y-axis. For that, you just plug in x equals 0. When you do that, g of 0 comes out to be 1. That means 0, 1 is the point where this upward opening parabola will be intersecting the y-axis. So this comes out to be the graph of x square plus x plus 1. Okay. It's now time to plot both the graphs of f of x, which is mod cos x, as well as g of x, which is this function, together in the same Cartesian plane. So let's begin. See, this is the graph of mod cos x. Right? Now in the same Cartesian plane, I'm going to draw that upward opening parabola, which is the graph of g of x. But before that, just listen to what I'm saying very carefully. See, you do agree that pi by 4 is greater than 1 by 2. Pi is 3.14 approximately. 3.14 upon 4 is definitely greater than half. Yes, so in here I can say if this is somewhere half, this is going to be pi by 4. Do you agree? Also, I know that cos pi by 4 is 1 by root 2, which is approximately 0.7, I can say. So if cos pi by 4 is 1 by root 2, that is approximately 0.7, cos half is definitely greater than 0.7. Yeah, for sure. And I also know that cos of minus theta is same as cos theta. So cos of minus half is same as cos half, which is definitely greater than 0.7. That means at minus half, the value of cos is going to be greater than 0.7. So minus half comma 0.7 is going to come somewhere here, which is under the graph of cos. This is the reason why when I plot the graph of g of x right now, it comes out to be this. Are you convinced? Nicely, right? Obviously, this point I've justified. This point, you know, the parabola was cutting the y-axis at 0, 1 and also 0, 1 lies on the graph of cos, right? That's why this is coming out to be a point of intersection. And hence, when you count all the points of intersection, how many are they? 1, 2. 2 points. That's it. Answer is option B2. That means there are two real values of x which are able to satisfy this equation because the LHS and the RHS, both these functions' graphs are intersecting at two distinct points when drawn together in the same Cartesian plane. Okay? Okay, then it's time to start with a fresh new topic, which is trigonometric ratios of compound angles. Now, what is a compound angle? Basically, a combination of two angles or three angles or finitely many angles is called a compound angle. So, if you add or subtract two or more angles, you end up getting a compound angle. For example, if A and B are two angles, then A plus B is a compound angle formed by A and B, and also A minus B is a compound angle formed by A and B. Our agenda is to find out the trigonometric ratios of these compound angles. And because these compound angles are formed with the help of these individual angles only, the natural curiosity arises that is there any relationship between the trigonometric ratios of these compound angles and the trigonometric ratios of these individual angles? If yes, what is it? Let's find out. Let's begin by computing the cosine ratio of the compound angle A minus B. For that, you consider a unit circle, which is a circle centered at origin, radius 1 unit. Now, on this circle, let R be a point such that OR makes an angle B with the positive x-axis in the anti-clockwise sense. Then coordinates of point R are going to be cos B, sine B. Right? Similarly, consider a point S on the circle such that OS makes an angle A with the positive x-axis in the anti-clockwise sense, and this will give me that the coordinates of S are cos A, sine A. Now, after all this is done, can you tell me what is the measure of this angle? Well, it's obvious. The measure is A minus B. Now that I know the measure of the angle A minus B, I am going to do a very smart step. I am going to deliberately consider a point Q on the circle such that OQ makes an angle of A minus B with the positive x-axis in the anti-clockwise sense so that the coordinates of point Q eventually turn out to be cos of A minus B, sine of A minus B. Yes? Now, in this entire process, what have I obtained? Let me share that with you. See, angle POQ is actually the angle subtended at the center of the circle with the help of the PQ chord of measure A minus B. Yes, similarly, angle ROS is also an angle subtended at the center of the circle by the RS chord again of the same equal measure A minus B. But I know as a matter of fact that only equal chords can subtend equal angles at the center of the circle, and hence I obtain that the length of the PQ chord is exactly same as the length of the RS chord. Isn't it? Now, if you just focus on the PQ chord, let me treat this as x1, y1, and let me treat this as x2, y2. Then, the length of the PQ chord using the distance formula comes out to be under root of x2 minus x1 whole square plus y2 minus y1 whole square. Agreed? Yes. Similarly, I am going to calculate the length of the RS chord. Focus on the RS chord. Now, suppose I take this as x1, y1 and this as x2, y2. Okay, so using the distance formula again, the length of the RS chord comes out to be under root of x2 minus x1 whole square plus y2 minus y1 whole square, and accordingly, I've plugged in the values. Right? Now that both sides of the equation are non-negative, I can very easily square both sides so that I can get rid of these square root sign which are really irritating me. Okay, so let me square both sides. This is what I'm going to get. Both sides are going to get free of the square root sign. Cool. Now let's proceed with solving what we've got. In here, this is nothing but it's like x minus y whole square. Okay, so it will be x square minus 2xy plus y square, and this plus sine square a minus b is kept as it is. Okay, so left hand side we are trying to resolve. Now let's move to the right hand side. Right hand side is cos b minus cos a whole square. Again, identity of x minus y whole square. It will come out to be x square plus y square minus 2xy. Similarly, I have plus sine b minus sine a whole square. Again, plus x minus y whole square, which is going to come out to be sine square b plus sine square a minus 2 sine a sine b. Okay, let's simplify this. Well, this is cos square of a minus b sine square of a minus b. You know cos square theta plus sine square theta is 1 for any angle which is theta. Cool. So cos square a minus b plus sine square a minus b is going to give me 1. This is minus 2 times cos of a minus b. Cool. And here I have a plus 1. So 1 plus 1 will make this 2. That is left hand side simplification. Let's move on to the simplification of the right hand side. Cos square b plus sine square b. Well, cos square theta plus sine square theta is 1 for any real theta. So cos square b plus sine square b will give me 1. Cos square a plus sine square a will give me 1 again. Minus 2 times cos a cos b. And minus 2 times sine A sine B. Yes, easy peasy calculation. 1 plus 1 will become 2, and hence this is what I get. Okay, let's simplify this further. So this 2 cancels out. I'm going to multiply both sides by a minus sign. I obtain 2 cos A minus B equal to twice of cos A cos B plus sine A sine B. 2 cancels out. What do you have? You are actually just left with what you wanted. The cosine ratio of the compound angle A minus B, which is coming out to be equal to cos A cos B plus sine A sine B, and bingo, we have obtained what we wanted, which is the cosine ratio of A minus B, coming completely in terms of the sine and the cosine ratio of the individual angles A and B. Got it? So, how to remember this? Well, if I treat A as the first angle, B as the second angle, then according to this formula, cos of first minus second is cos of first into cos of second plus sine of first into sine of second. Okay? Using this, let's try to compute the cosine ratio of another compound angle, which is A plus B. Right? For that, realize that A plus B can actually be written as A minus minus B. And hence cos of A plus B comes out to be this. Now in here, if I treat this as the first angle and minus B as the second angle, I can apply the formula cos of first minus second, which is cos of first into cos of second plus sine of first into sine of second. Right? Now what is coming into picture in here? Just see. Cos of minus B. I know cos of minus theta is same as cos theta. So cos of minus B will be replaced by cos B. And also I know sine of minus theta is minus sine theta. Sine pulls out the minus sign, whereas cos absorbs the minus sign, right? So this will be minus sine B. And hence this complete step transforms to this. Okay, so what do you obtain? That cos of A plus B is equal to cos A cos B minus sin A sin B, or an efficient way to learn this is treat A as the first angle, B as the second. So cos of first plus second is cos of first into cos of second plus minus sin of first into sin of second. Got it? Now that we've derived the formula for cosine ratio of sum of two angles as well as cosine ratio of the difference of two angles, let's check out this application. See in here, you can see an expression which is cos 31 degrees plus cos 89 degrees plus cos 151 degrees. Your task is to find the value of this expression. What is it equal to out of the given four options? So in here, we basically have to focus on simplifying this expression given to us, and it's but obvious that the simplification can happen only with the help of these angles. Isn't it? Because the trigonometric ratio is same throughout. It's cosine. So can you say any connection between these three angles? Try to think upon this. Is there any connection between the three given angles here, or are they just given randomly? Well, I think 89, yes, can be written as 120 degrees minus 31 degrees. Yes. And 151 on the other hand, I can write it as 120 degrees plus 31 degrees. That means now one thing is good, that all the angles are written in terms of 31. Isn't it? Okay, what next? Well, right now if you look at these angles, they are not some integral multiples of pi by 2 plus minus theta, or they are not some integral multiples of pi plus minus theta. They don't look like allied angles. So we can't use the concept of trigonometric ratios of allied angles in here. So what to do? Well, if I'm not wrong, focus on this term. This looks like cos of difference of two angles, isn't it? So if I treat this as A and treat this as B, I know this term will boil down to cos A cos B plus sin A sin B. Yes? Similarly, look at this term. Okay? This looks like cos of sum of two angles. Let's call them A and B. Then this will boil down to what? Cos A cos B minus sin A sin B. I've just used the two formulas which we've recently derived. Yes, now let's simplify this, okay? Fine, well, this is plus sine 120 into sine 31. This is minus sine 120 into sine 31. So both these terms will obviously get cancelled out. Okay, what are you left with? Cos 31 as it is plus twice of cos 31 into cos 120. Easy peasy, isn't it? Okay, let's proceed ahead. Out of the three angles that I can see over here, out of which two are 31 and one is 120, this 120 is familiar to me. Why? Because 120 is actually an allied angle. How is it allied? Well, I can write 120 as 90 plus 30. And I know what is cos 90 plus theta, where theta is acute. What is it equal to? It is minus sine theta. Why minus sine theta? Well, co-function of cos is sine. Okay, and 90 plus theta lies in the second quadrant. That's why minus sine. Why? Because cos is negative in the second quadrant. Okay, sine 30 is 1 by 2. So minus sine 30 gives you minus 1 by 2. What next? Well, this becomes cos 31 minus 2 upon 2 cos 31. What is this? Obviously 0. So, the expression which was looking pretty scary to us, whose value we had to evaluate, is coming out to be 0. See, straight away these three angles are not at all familiar to us. We can't directly compute their values. And that is where the cosine ratio of the sum of two angles and difference of two angles comes into picture to help us and get to the answer. Well, after computing the cosine ratio of the two compound angles A plus B and A minus B, it's now time to move on to computing the next trigonometric ratio, that is sine ratio of the compound angle A minus B. So according to our setup, do you agree that I can write sine of A minus B as cos of 90 minus A minus B? Yeah, do you agree? Cos of 90 minus theta is same as sine theta. Yeah, we've learnt it. Now, allow me to manipulate this a bit. I am going to deliberately write it as 90 minus A as one angle plus B. So in here, what gets created is, this is acting like my first angle, this is acting like my second angle. So what do I have? I have cosine ratio of the sum of two angles, which I know is what? Cos of first into cos of second minus sine of first into sine of second. Yes. Now in here I have cos of 90 minus A. Here I have sine of 90 minus A. Well, I know cos of 90 minus theta is sine theta. And I also know sine of 90 minus theta is cos theta. We've learned all this in allied angles, okay? So I'm assuming your concepts about trigonometric ratios of allied angles are extremely clear. Based upon this, I'm going to replace this by sine A and replace this by cos A. When I do that, what am I left with? I'm left with sine A cos B minus cos A sine B. Bingo. The sine ratio of the compound angle A minus B is coming out to be sine A cos B minus cos A sine B. Okay, you can remember it as, again, the same way. Treat this as first angle, treat this as second. Sine of first minus second is sine of first into cos of second minus cos of first into sine of second. Okay? Obviously, now we're going to move ahead to calculate the sine ratio of the sum of two angles A and B. Okay? What will this be equal to? Well, same thing. I'm going to write A plus B deliberately as A minus minus B. Yeah? Now, this is like my first angle, minus B is like my second angle. So, I am going to use the formula sine of difference of two angles. Is what? Sine of first into cos of second minus cos of first into sine of second. Okay, now recall cos of minus theta is same as cos theta and sine of minus theta is minus sine theta. So this gets converted to cos B and this gets converted to minus sine B. This minus and this minus will together combine and become plus. Eventually I will be left with sine A cos B plus cos A sine B. This is the formula for sine of A plus B. Got it? So again, treat this as the first, treat this as the second angle. You know what is sine of first plus second. It is sine of first into cos of second plus cos of first into sine of second. Got it? So now you even have the sine ratio of the two compound angles A plus B and A minus B with you. Well, it's now time to check out this wonderful application. As you can see in here, we are given an equation and we are asked to prove it. So if I'm not wrong, this given equation technically has two parts to it. First is this, second is this. Let's begin by focusing on the first part of this equation, which is straight away demanding from us the sine ratio of the angle 5 pi by 12. Now the problem is, directly I don't know the value of sine 5 pi by 12. So obviously the strategy is going to be to break 5 pi by 12 up into smaller angles, that too, if possible, familiar angles, standard angles. Let's see if that's possible or not. Now 5 pi by 12 is nothing but 5 into 180 by 12, which is 5 into 15, which is 75 degrees. That means 5 pi by 12 is an acute angle actually equal to 75 degrees. Now can you think of 75 degrees being written up as sum or the difference of any two familiar standard angles? Can you do that? Think? Well, it's extremely simple. This can be written as 45 degrees plus 30 degrees, where both 45 and 30 are actually basic angles whose sine, cosine, tan, any ratio we know very, very nicely. Yes, so once I have written 5 pi by 12 as pi by 4 plus pi by 6, which is 45 plus 30, my sine 5 pi by 12 transforms to sine of A plus B, where A is pi by 4 and B is pi by 6. And now, well, this is enough a hint to use the identity sine of a plus b is sine a cos b plus cos a sine b. So expand the right hand side using this particular formula. You get what? You get an expression involving sine and cosine ratio of these angles, which of course you remember at the tip of your tongue, isn't it? Sine pi by 4 is sine 45, 1 by root 2, cos 30 is root 3 by 2, cos 45 is 1 by root 2, and sine 30 is again 1 by 2. On simplifying this, you get root 3 plus 1 by 2 root 2, and bingo, the first part of your equation is straight away proved that the value of sine 5 pi by 12 is nothing but root 3 plus 1 by 2 root 2. Now it's time to focus on proving the next part of this equation. So let's see. Well, I already have the value of sine 5 pi by 12 and I want to fetch the value of cos pi by 12. So, obvious curiosity arises, is there any connection between these two angles? Is there? Let's see. 5 pi by 12 came out to be 75 degrees and pi by 12 is 180 degrees by 12, which is simply 15 degrees. Well, straight away, if I try to add 75 and 15, I end up getting a 90. That means, of course, there is a connection. These two are complementary angles, which means I can straight away write 15 degrees as 90 minus 75 degrees. That means if I convert it into radian, because originally my angles are given in the radian measure, what do I get? Pi by 12 is actually pi by 2 minus 5 pi by 12. What do I want to compute? I want to compute cos pi by 12. Okay, not a problem. Which will be equal to cos of pi by 2 minus 5 pi by 12. Wait a second. What did we just get? Cos 90 minus theta, where theta is 5 pi by 12, which is 75 degrees, which is acute. I know when theta is acute, cos 90 minus theta is equal to sine theta. That means what? Cos pi by 12 is actually nothing but equal to sine 5 pi by 12 only, whose value we just computed, which came out to be root 3 plus 1 by 2 root 2. That means bingo. We were thinking initially that we have to find the value of sine 5 pi by 12 as well as cos pi by 12. But the great thing is they both have the same value equal to root 3 plus 1 by 2 root 2. And that's the fantastic observation about this question. Well, let's now quickly recollect all the formulas that we've learned till now. The first one is the cosine ratio of the compound angle A minus B, which is equal to cos A cos B plus sine A sine B. The next one is the cosine ratio of the compound angle A plus B, which is equal to cos A cos B minus sine A sine B. So what did you focus on? Here it's minus, here it's plus, here it's plus, here it's minus. That means in the case of cosine ratio, the sign alternates. Third formula was sine of A minus B is equal to sine A cos B minus cos A sine B. And the fourth formula we learnt was the sine ratio of the compound angle A plus B, which is sine A cos B plus cos A sine B. You can notice minus, minus, plus, plus. That means in the case of sine ratio, the sign doesn't alternate, it remains the same. We know as a matter of fact that cosec is nothing but reciprocal of sine. Using this fact, you can compute the cosec ratio of the two compound angles A minus B and A plus B. Similarly, you know sec is nothing but reciprocal of cos. Using this fact, you can compute the sec ratio of the compound angles A plus B and A minus B. What about the remaining two ratios, the tan and the cot ratio of A plus B and A minus B? Let's find that out. See, tan of A plus B is something that I want to find out. But I know as a matter of fact that tan of an angle exists only and only when that angle is not an odd integral multiple of pi by 2. Do you remember? Yes, that means tan of A plus B will exist as a real quantity only when A plus B is not an odd integral multiple of pi by 2. Okay, but along with that, I am also taking into consideration that a and b individually also should not be any integral, odd integral multiple of pi by 2. Why am I doing that? You'll get the answer of this just in a short while. Just be patient. Let's begin finding out the value of tan of a plus b. I know tan is nothing but sine upon cos. So tan of a plus b comes out to be sine of a plus b upon cos of a plus b. Well, I can replace this by sine a cos b plus cos a sine b, and similarly I can replace this by cos a cos b minus sine a sine b. When I do that, this is what I get. Now my next step is very, very smart. I am going to divide both numerator and denominator by cos A into cos B. But wait a second. I can divide by this. I did consider A and B individually to be not odd integral multiples of pi by 2. That means I made sure cos A is non-zero and cos B is non-zero, and hence the product of cos A and cos B is also non-zero, and hence, check, I can divide the numerator and denominator by cos A cos B. It's a valid step. So let's begin doing that. Sin A cos B divided by cos A cos B plus cos A sin B divided by cos A cos B upon cos A cos B divided by cos A cos B minus sin A sin B divided by cos A cos B. Because cos A individually is non-zero, cos B individually is non-zero, I can cancel this out. Further, this also cancels out. What am I left with? Sin A upon cos A is tan A. Sin B upon cos B is tan B. This is nothing but 1. And what is this? Sin A upon cos A tan A. Sin B upon cos B tan B. That means eventually this turns out to be tan A plus tan B upon 1 minus tan A into tan B. And bingo, this is the very tan ratio of the compound angle A plus B. Got it? So what do you understand? The tan of first angle plus second angle is tan of first plus tan of second whole upon 1 minus tan of first into tan of second. Now I'm interested in computing tan ratio of the compound angle A minus B. Well, it's very simple. I can first of all rewrite A minus B as A plus minus B. Yes, so tan of A minus B comes out to be tan of A plus minus B. Do you agree? Now I'm going to treat this as the first angle and minus B as the second angle. I know as a matter of fact that tan of first plus second is tan of first plus tan of second whole upon 1 minus tan of first into tan of second. Right? Now tan of minus theta is minus tan theta. That means this part eventually boils down to minus tan B. Similarly, this also becomes minus tan B. This part. Okay, so this minus and this minus becomes plus. Eventually this expression boils down to tan A minus tan B upon 1 plus tan A tan B. That means tan ratio of the compound angle A minus B is obtained. How are you going to remember this? Again, same strategy. Tan of first minus second is tan of first minus tan of second upon 1 plus tan of first into tan of second. Now that we've obtained the tan ratio of the compound angle A plus B and A minus B, keeping in mind that this exists only when A plus B and A minus B satisfy the constraint of not being an odd integral multiple of pi by 2, along with A and B also satisfying the same constraint. Now let's move ahead to talk about the cot ratio of the compound angle A plus B. But again, we know as a matter of fact that cot of an angle exists as a real quantity only and only when that angle is not an integral multiple of pi. So in here, if I want to talk about cot of A plus B, I have to make sure that A plus B is satisfying the restriction of not being an integral multiple of pi. Along with that, I also individually want cot A and cot B to exist. So A and B, I also want to satisfy the restriction of not being an integral multiple of pi. Okay, well, I just computed tan of A plus B. And I know the very beautiful connection between tan and cot, that they both are reciprocals of each other. I'm going to use this fact to get the cot of A plus B formula from tan of A plus B formula. But again, be cautious, because I am considering tan of A plus B formula, I am not saying it, but this is an unsaid assumption here that a plus b is not an odd integral multiple of pi by 2. A and b individually are also not equal to any odd integral multiple of pi by 2, because otherwise this formula will not exist. Okay, kept in mind? Now, because tan and cot are reciprocals of each other, I can write tan as 1 upon cot. So when I do that, in this formula, everywhere, what do I get? Well, left hand side becomes 1 upon cot of a plus b. Tan a is replaced by 1 upon cot a. Tan b by 1 upon cot b. Denominator becomes 1 minus 1 upon cot a into 1 upon cot b. Now it's time to just simplify this expression. It's very simple. Numerator boils down to cot b plus cot a upon cot a cot b, and denominator boils down to cot a cot b minus 1 whole upon cot a cot b. Because I said that it's not written, but a and b individually are also not odd integral multiples of pi by 2. That means cot a and cot b individually are not equal to 0, which means cot a into cot b is also non-zero, and hence I can cancel this out straight away. So what am I left with? I'm left with cot a plus cot b whole upon cot a cot b minus 1, and bingo, this is the formula for the cot ratio of the compound angle a plus b. We're going to remember it as cot of first angle plus second is cot of first into cot of second minus 1 whole upon cot of first plus cot of second. Now let's compute the cot ratio of the compound angle a minus b. This is extremely simple because I'm just going to write a minus b as a plus minus b. So this makes this cot of first angle plus second angle. Okay, we know what this is equal to. It is cot of first into cot of second minus 1 whole upon cot of first plus cot of second. Now please recall cot of minus theta is minus cot theta. So cot of minus b will become minus cot b everywhere. So the complete expression boils down to this. And now I'm going to take out minus sign common from the numerator and denominator and cancel it out so that I have a more simplified version of this expression, which is cot a cot b plus 1 whole upon cot b minus cot a. Got it? And hence you obtain the cot ratio of the compound angle a minus b as well. What is it? Cot of first minus second is cot of first into cot of second plus 1 whole upon cot of second minus cot of first. Got it? So 4 more formulas we've learned. First is tan of the compound angle a plus b, which is tan a plus tan b upon 1 minus tan a tan b. Second is tan ratio of the compound angle a minus b, which is tan a minus tan b whole upon 1 plus tan a tan b. So if there's plus on the left hand side, there's plus in the numerator and opposite minus in the denominator. If there's minus on the left hand side, there's minus in the numerator and opposite plus in the denominator. Exactly opposite happens in the case of cot. Cot of a plus b is cot a cot b minus 1 whole upon cot a plus cot b, and cot of a minus b is cot a cot b plus 1 upon cot b minus cot a. Do you understand? So we have in totality talked about 8 formulas in this session. Sine and cosine ratios of a plus b and a minus b, tan and cot ratios of a plus b and a minus b. Trust me, I can't stress upon the importance of these formulas enough. You have to memorize these formulas by heart so that anyone asks you tomorrow, you should be able to tell it at the drop of a hat without any delay. That's how important these formulas are. I'm going to talk about more concepts related to compound angles in the next session. I'll meet you then very, very soon. Till then, you take care and keep learning.